So my name is Saveria, and I'm going to present you this talk about quasi-static and fatigue properties of 316L alloy fabricated via MIAM. So I will structure the presentation like this. First, a quick description about the process. Then I will describe specifically what we did to fabricate the specimens that I will show you today. And then I will present the results for two batch of results, one for tensile tests and one for axial fatigue tests. So we can start with material extrusion. It is actually a three-phase process, and the additive manufacturing is only the first phase, the printing phase. Then we have the binding and sintering. The printing phase can be done with one of those printers that I assume everyone knows. So they can be used also for non-engineering purposes, and mainly the feedstock material is plastic, PLA. But we can use a special filament that contains metal powder. So it's metal powder and a polymer that serves as a binder. And you can see here a cross-section of the filament that we used. The composition is heterogeneous. So the printing phase, the outcome of the printing phase is just a green part, which has a mixed composition, both metal powder and polymer. Then we have the debinding to remove the binder, and this can be done either with chemicals or with a thermal cycle. And then we have the sintering process, in which the metal powder can diffuse, create necks, bonds, and then the grain boundary is set in. So what we did, we used one of those printers and a filament that contains 316L metal powder. And for these experimental campaigns, we wanted to produce these cuboids, so very simple shapes. You can see the CAD models, the green part in the middle and the final parts, and we printed them into orientation, flat and standing on the printing platform. The tuning process of the printer process was actually quite demanding. So here I've listed just the main printing parameters, but there are many more that one can change. And the reason to print these cuboids is to obtain different types of specimens. So we machine the specimens from the cuboids using the EDM machine, and we obtain front, top, and side specimens, changing the extraction direction and the orientation of the cuboids. So what is the difference? The front specimens have the layers that build up through the width. Then the top specimens have the layers that build up through the thickness. And finally, the side specimens have the layers building up through the length. So first thing first, we perform tensile tests. So we have here the top specimens. And I think it's quite clear. You can see there is a lot of discrepancy, both in terms of strength and in terms of elongation to fracture. And this suggests that the procedure is not really repeatable. Then we have the front specimens, and the front specimens are generally characterized by longer elongation to fracture. They are able to allocate more plastic deformation. And then we have the side specimens. Here I just shaded the areas to help you locate the side specimens. They are generally weaker, and they also tend to fail at an earlier stage of the test. So these are the numbers of the tensile properties, but I think it's more interesting to check the fracture mechanism. And so we perform in situ tensile tests in an SEM microscope. So we can start with the top specimens here. First, you can see that you can understand what is the printing strategy that we used, which is a classic plus minus 45 degrees. And in the case of the top specimens, basically, the fracture just followed the easy path of the interface between raster. That means that the adhesion between raster is not sufficient, clearly. Then we can jump to the side specimens. Here, the issue was that, as you can see, there is quite a lot of porosity, and the porosity patterns comes once again from the building or the printing strategy that we obtained. These are fracture pictures, so of course the pores enlarged and deformed, but also in undeformed condition, it was quite clear that there were a lot of pores. And here the fracture is quite quick because it's sufficient to follow an alignment of pores, and that's why they tend to fail earlier. And finally, we have the front specimens in which actually we can see some classic signs of ductile fracture. So we have elongation, quite a lot of elongation before fracture, localized reduction area, the dimples in the fracture surface. And we also saw that there are a lot of inclusions that probably comes from the powder atomization process, and they stay in the specimens and they favor the void enucleation. Okay, so then we did axial fatigue tests following the same procedure. So here we have SN curve, load ratio 0.1 for the top specimens, the front specimens, and the side specimens. And what can we say? We can say that strictly speaking about statistical fatigue limit, there isn't a significant difference between building orientation, but the impact of the building orientation is more visible in the area towards the low cycle fatigue area. And this is probably related to the tensile properties that I showed you before. But once again, the difference is more visible in the fracture mechanism. So basically, the top specimens, again, we can see the pores alignment, and it is difficult to identify a killer defect. It's most likely that there were multiple crack initiation points, while the front specimens are significantly more dense, and usually we could find the killer defect that was either on the surface or worst surface plus subsurface defect. And finally, we have the side specimens, in which again you see the rasters, the inclination of the rasters. And here, again, it's difficult to specifically realize if the fracture is the crack started from the surface or from an internal pore. To conclude, we can compare our material to a reference material. And speaking about tensile tests, the closer to these requirements, to these target values, are top and front specimens. While for the fatigue tests, it's more difficult to make a proper comparison, but still we can infer that 316L should give more in terms of fatigue resistant. And summing up these results of this investigation about building orientation on material extrusion, additive manufacturing, about tensile tests, the major impact is on the ability of the specimens to allocate the plastic deformation and on the fracture mechanism. And for the axial fatigue tests, the same, the fracture mechanism are affected by the building orientation, while the fatigue limit itself is not so significantly impacted. On top of this, we also realized that the building orientation affects the residual porosity, apparently. So this needs further investigation, and this is an issue that needs to be counterbalanced somehow. So this was it from my side. Thank you.